this is our second lecture on design of plate girders. Plate girders, as I told you in the previous lectures, are actually flexure members, and they are actually built-up members because they are built up on the demand. They have got long flanges and they have got a very deep web or stems, and actually they perform the function of deck of any bridge of mega bridges. So I mean, it is a flexure member, but it's a very big flexure member compared to, I mean, the ordinary flexure member we have in our building is our beams, but conversely, this plate girder is actually a very long flexure member. So I mean, in the previous lecture, I told you something that a very long flanges are being supported by these deep stems or web, and obviously as it is very long in this direction, so we require some lateral stiffness because we have to prevent the lateral buckling. So buckling requirements are also taken into account while designing these. This figure is very important because it tells us about the slenderness of our plate girder. So actually this x-axis depicts slenderness ratio, and we had to find two values, lambda p and lambda r, and based on these two values we have to actually we had to decide, or we had to decide what we are actually in, which zone we are in, compact zone, in cylinder zone, or we are in non-cylinder or non-compact zone. That is our design is compact, our design is slender, or our member is slender or compact, elastic, inelastic. So actually this is the slenderness ratio, and this is y-axis depicts the moment. In compression members, in previous lectures, there was only one value, lambda r, and it was about 4.71 E by Fy, if you remember. So we had to decide based on this value that either we are in the cylinder zone or we are in the compact zone. Okay, next, for example, now this is our question, and we have to find the moment capacity of this plate girder, and some data is given, and data is this is the yielding stress of the steel, I mean the steel of which this plate girder is made up of, and also this is the section modulus. You should know that there are two types of section modulus, elastic section modulus and plastic section modulus. So here the elastic limit is acceptable and plastic design is required. Here you are in the elastic zone, and the plastic failure is not required or is undesirable. Actually, whatever the case is, S is equal to I, that is second moment of area or moment of inertia, divided by neutral axis of that member or of your structure. So I by C or I by Y, and you know the unit for I is inch to the power 4, and if it has the unit of inches, so you get cubic inch. So it's same, I mean inch cube or cubic inch is the unit for SX, that is elastic section modulus. Okay, this is the data, and yes, one more data. So this is your plate girder. It has got very long flange and deep web or deep stem, and you have got fillet wells, and we have studied the wells in the previous lectures, in our very first lectures. Some requirements, lateral buckling requirements are also given, like the stiffener used is 4.5 inches into 3 by 8 inches. It means this length is 4.85 inches, and the stiffener, if you look from here, I mean this is your eye, and if you're looking from here, so you will see a stiffener like this. So its thickness is 3 by 8 inches. I mean, it would not be required in this lecture, but I mean, it's very good to get informed on the type lateral buckling requirement of a plate girder. Also, you have got some 5 feet probably, or inches, I don't see it, but it's 5 feet. So a second stiffener is provided at the length or distance of 5 feet. So so on, the stiffeners are provided in this direction. But this is not required, but this is a question. You should be knowing about the components of any plate girder. Okay, the depth of flange, this is flange, is 1 inches, and the thickness of this web is 1 by 4 inches. Okay, overall depth is 40 inches, and you have to find the available, because this is a flexion member, so you should be knowing about the moment capacity of this plate girder. The shear design is not here. It would be discussed in future lectures, and it is one of the important part of designing of plate girders. Okay, the question starts here. First of all, we have to check the slenderness ratio of web and flanges. You should remember that in the previous lecture, our flange was slender. So the question is here. In the previous lecture, the web was compact. We first found out the compactness or slenderness ratio of our web, and based on these values, we found that our web is compact. However, our flange was slender. Our flange was slender. So it was a previous lecture. So in this lecture, first of all, we have to find the slenderness or compactness of our web. So this is, W is for web, and this depicts the slenderness ratio. So HC by TW, this is 40 inches. So you are dealing with your web, right? 40 inches divided by thickness of your web is 1 by 4 inches or 0.25 inches. So you find out, you calculate it to be 160, right? Now the lambda r value and lambda p values, for web you have to find that. For the lambda r value, this is, while checking the web compactness, the lambda p value should always be lesser than lambda r. So lambda r is 5.70 and lambda p is 3.70. So here lambda p would be, you should be calculating this 3.70 e by fy. Lambda r is 5.70 e by fy. So it comes out to be 137. Lambda r is 137. So obviously, because lambda p contains 3.70, it would be much lesser than 137. Our case is, our lambda w is 160. The slenderness ratio of this web is 160. So it is very much greater than 137. That is, lambda w is greater than lambda r. So you are somewhere, you should know that this is lambda p and this is lambda r, and this was the slender zone and this was the compact zone. It means your web is slender because your lambda r comes out to be 137 and the lambda w is 160. It's much greater than 137. It means your web is slender. Now it's a problem, so we have to design based on slenderness of our web. But before that, first of all, as we performed or checked the slenderness of flanges in our previous lecture, let us first calculate the slenderness of flange of your plate girder. So these two values, lambda p and lambda r, for to compute the slenderness ratio of flange, the upper and lower bound values are these two, and You should know that this is lambda r and this is lambda p. So I mean you get three zones. This is compact, this is slender, and this is non-compact or non-slender zone. Um, now, I mean it's very easy. Lambda p E by Fy, E should be 29,000. Fy is given, it is 50 ksi, and here Kc, the Kc is 4 by x. I mean it was computed in the previous lecture. It is actually the height of your web and thickness of your web. uh, lambda f is very important. Likewise, like we computed the lambda whc, this height divided by its thickness. While calculating the lambda f, the formula used should be bf divided by 2tf. So if it is 10 inches, okay, this is 10, so 2, and thickness of your flange, this is the depth or thickness of your flange, tf. So 2 into 1, so we get 5. Okay, lambda f is 5. Okay, and if you look here, your lambda f is 5, your lambda p is 9.15. Lambda p is 9.15, and lambda r, I mean it is 0.95 into lambda r. Okay, uh, if you look here, this is your lambda r and this is your lambda p. All lambda f is, and you have found out that your lambda p value is 9.15. So if you compute lambda r, it would be much greater than 9.15. So you can compute it here from here, lambda r. It's very easy. Lambda r 0.95, kc is given, that it is, you can calculate it. That is 4 divided by hc by tw. Hc by tw is 160. So it would be 160 here. So you will be getting kc value, and you will put back here and you will get lambda r. So you will find that lambda r would be much greater than 9.15. So you should compute this. I mean it's your job to compute lambda r. It's very easy. The formula used would be 0.95 kce by fy. Kc is this. But we found out that our lambda is f is 5. So it is much lesser than this lambda p. So I mean it is very clear cut, and it is obvious that we are in the compact zone. So I need not find this lambda because I have found out lambda p, and by logic lambda p should always be less than lambda r. It states that. I mean you can compare these two values and you will always find that lambda p is less than lambda r. So I have just computed lambda p and found out lambda f, and I found out that I am in the compact zone because my lambda f is less than lambda p. This is 5 and this is 9.15. 5 is always lesser than 9.15. It means, now the case is, now understand the question. The case is my web is slender, and you know what slender is signifies. This is lambda r, lambda p. So I am somewhere in the slender zone when I am dealing with my web. So my web is slender. It means it is too long or too deep, and the thickness is very small. I mean, if you have two columns, for example, these two, and this. Now, if you apply a compressive load, for example, I'm giving you an example. So you will see that it would buckle first compared to this because it is slender. It is non-compact. It is compact. It is compact and non-slender. It is slender or non-compact. It means this is too slender and this is compact. So this is the logic. I mean, in this case, my the stem, depth of my stem or web for this plate girder is 40 inches, and its thickness is very small. I mean, it is 0.25 inches, quarter of an inch. It means it's slender. Okay, now when I'm dealing with my flanges, now I find that my flange is somehow compact and it is non-cylinder, and I easily found out using the formula TF divided by 2TF. So I found out that this protruding or projecting length is not so much. If it was much longer and much thinner, then it would have been a slender flange. Now, I mean, if I again let me explain it to you in detail. Okay, this is 1 inch and this is 10 inches. Next case is I have a flange, and the flange case is like this. Here it is 40 inches and 1 inch is same. Now you see that its depth or thickness is 1 inch and its length is 10 inches. It means it's not too much thin, or you can easily find out its value. The lambda f is equal to bf divided by 2tf. However, in this case, the length is too long. It means if a load, under any load, under compressive load or under flexure load, it would be prone to buckling. It may buckle. Somehow it may buckle because it is slender. Because length has been increased and accordingly the thickness was not increased. Here the compactness can be seen because length is optimum and length is optimum and depth is optimum. The thickness is also optimum. Here the length is too long but the thickness is very small, 1 inch. So this is the case. I mean, in our question, the web is our web is slender and flange is okay. In the previous lecture, I mean, I told you and we found out in the previous lecture, the lecture is here. The web was compact, however, the flange was slender. So what we did, we used this formula. So this formula would be used when your flange is a problem. It means your flange is slender compared and web is okay. And what if now here the flange is compact but web is a problem or web is slender? So I'll be using this formula. Again, this is a moment. This is your section modulus. This is your yield stress. This is strength reduction or moment reduction factor. Actually, the problem is your web is slender. So web is slender. It cannot resist the longer. I mean, it cannot resist the larger moments. That's why I have to reduce the moment. The maximum moment can be 1. I mean, it is the max. So you have to reduce it accordingly. So you have to use a formula for RPG, and you need not remember it because it is always there in the codes. The formula is this, a very easy formula. Here 1200, 300, these are constant, and this you have already found out. This is very easy. This is 5.7. This is, I mean, you should be knowing that 29,000, and this is 50 ksi. And this AW is actually AW into AF. This is the area of web and the area of flange. Area of web, yes, area of 10 into 1. Area of this stem 40 into 0.25. So it's very easy. You have just put the formula and you found out that RPG is 0.985. It means the moment actual, if you did not use this RPG, then the simple formula would have been Fi into Sx. But as the web is slender, so we have to reduce this moment. So we'll multiply it with rpg, and you know what rpg is. Rpg is 0.985. Finally, you will use this two factors, well-known factors, factor of safety and resistance factor, phi, phi or phi, and you will find out that the moments are, your plate girder is able to resist these much moments. Okay, finally, I think we have dealt with two cases. The first case was in the previous lecture when our flange was slender and web was compact. In this question, web was slender and flange was compact. So, I have just summarized these. Yes, this is actually the summary of design of plate girders. In the next lecture, inshallah, we'll be doing. Okay, you should be knowing that we have dealt with the flexure capacity. We have been able to find the flexure capacity of plate girder. So in the next or upcoming lectures, we'll be dealing with the shear design of plate girders. So this is the summary. If your web, check the web or compactness or slenderness. If web is slender, use this formula. Check the flange compactness. If the flange is slender, use this formula. And for lateral torsional buckling, the previous lecture involved some lateral torsional buckling phenomenon. So this was the formula. So this is actually the summary. So I have attached this slides with the lecture. So inshallah, I hope that you must have understood this lecture. Inshallah.